Good day, stat students. So we're going to cover section 2.3 today, and we're going to take a look at measures of center. So basically, we want to know where the center of the data is located, and there's different ways of measuring that. And so I'm sure you've heard of all these before, okay? And so the first measure of center that we'll take a look at is a mean, and as you might know, that's just an average to the median. And 3, many textbooks, not this one, would throw the mode in there. This textbook pretty much just focuses mainly on the mean and the median being a measure of center, but the mode is also thought of in a lot of textbooks, a lot of stats books. They'll throw the mode in there too. Okay. Now we've already talked about the mode, so we're going to focus more on the mean and the median today. So the mean is the sum of the observations divided by the number of observations, and so that's in words, right? And so, example of calculating. So what is this? This is the balancing point for all your values in your data set. Okay, that's what the mean is. And so let's do an example calculating the mean. Now, I'll just kind of warn you here is that I'm sure a lot of you already know how to calculate a mean, how to calculate an average, but don't fall asleep here because there's going to be extra information that you will need for statistics. All right. So let's find the mean number of siblings for 10 students. And so the following is the data. Okay. And so here, let me get my pen out. So here we have 10 students. Okay. And here were their responses. And so this was a real data set. Okay. I just asked the first 10 students in my class one day, a while back, and that was the answers that I was getting. So X is the number of siblings, okay? And so if we had to describe it to maybe like a 4th grader or 5th grader, and they're calculating average for the first time, they would go about it calculating the average by taking the sum of the observations divided by the total number of observations. So in words, there you go. However, in mathematics and certainly in statistics, we like to use symbols to stand for this stuff. And so when we write out equations, because those equations would get really long and verbose if we had to write it out in words, and so we have to use symbols here. Okay. And so this is our first example of a formula using symbols. All right. So a mean, the way we would calculate it is that we would go ahead and take the summation of x divided by n. So if you've never seen this before, if you've never seen this symbol before, what that is, that's a capital sigma sign. Okay, capital sigma sign. It's a Greek letter. And anytime you see that in a formula, it means to sum. Okay? It means to sum something. Okay? And I will guarantee you this, okay, is that if you see a summation sign in a statistics formula, what that's telling you is that there's not just one x out there. There's many x's, all right? And so, in algebra, we're used to seeing that x just stands for one specific value. However, if you see a summation sign in a statistics formula, I almost guarantee you that that means that there's more than just one x out there. And so what we have to think of, let's go over to the data over here. So we had 10 students. So what we got to think of is that 3 is actually x1, and the 0 is x2, and so on and so forth. x3, x4, down through x10. Right? And so anytime you see a summation sign in statistics, that's telling us that there's multiple x's out there that we have to do something with. Now, it doesn't always mean to just add up x, okay? But I guarantee there's multiple x's out there to do something with in that formula. Here, it's just saying add up all the x's. And so we would add up all these x's and divide by n. Now, what's n here? N is what we call the sample size. And it is really important to memorize these symbols because we're going to have a little bit more complex formulas here. And if you do not know what these symbols stand for, not alone what their name is, but what they stand for. Okay, so N is the sample size, and it stands for the total number of observations. You can't do a lot of these formulas. You can't do what we are asking you to do and what you need to learn. Okay, and so please keep this in mind, is that you do need to memorize the symbols ASAP. Okay, X stands for the values of our variable. The summation sign stands for in mathematics to add or sum something, and N is our sample size. How many people did we ask? All right, or how many things did we sample? All right, our sample size. All right, so let's do the actual calculation. So maybe get your calculator out, pause the video, get your calculator out, and add these numbers up. Okay, or maybe you can do it in your head. Then once you're done, come on back. So hopefully you've done that, and I got 31 for the sum here. Okay, and N is 10. Now why is it 10? Because we had 10 students, right? We had 10 observations for X. Okay, and so I got here 3.1. Now there's a couple of things here. A lot of times students go and say, okay, so we got 3.1, and X was in terms of siblings, and X is generally thought as a discrete variable. I know some of you could have like half siblings, but let's say that we were talking about natural siblings here, all right? And so a lot of times what I see on test from one student or maybe two students is that they'll say, okay, it turned out to be 3.1, and they'll say that means it's approximately 3. No, don't do that. Averages, means, can take on a decimal. All right, it can have a decimal in it. So for instance, have you ever heard of like there's 2.5 children per household in the United States? That's an average. All right. Now I'm sure we don't have any half children running around anywhere. Okay, but notice they didn't round it. They left it as 2.5 children. Leave it alone. Okay, so if your mean turns out to be 3.1, leave it. Okay, leave it alone. All right, and don't say it's approximately this or approximately that. Okay, so what would we put for the units here? Well, whatever the units of X is. So since X is in terms of siblings, we would say 3.1 siblings. All right. All right, and then I'm going to take your focus over to here. All right, what does that 12 look like to you? Does that seems like an extreme value. Now, back in this was real data, and this came from a gentleman who was quite a bit older than your typical college student. And, you know, back in the 50s, maybe even the 60s, it wasn't all that crazy to hear that somebody had 12 siblings, okay? And so what would that be considered? That would be considered an outlier, okay? Extreme value. And so we saw that, we had that quick little discussion with regards to outliers and identifying with the graphs. Certainly we can see it here, okay? But how is the outlier affecting the mean? Well, what happens is that, generally speaking, outliers will pull the mean towards itself or themselves, okay? And so let's go back to the data here for a second. So if you looked at the first 9 observations here, would any of you I don't think anybody would have said, the average is going to turn out to be 3.1. I don't think that really makes sense, because remember, this is the mean should be the balancing point between these numbers, okay? So what did this 12 do to the mean? It made it larger, okay, than what we expected it to be, all right? And so because the outlier was larger than your typical values, it made the mean larger. If your outlier is smaller versus your typical values, that means it's going to make the mean smaller. It's going to pull on it. Okay, and graphically we can see this maybe here a little later on with a graph. Okay, so there's 2 means that we will deal with in this course. There's a sample mean, which is a statistic. Why is it a stat? Because it's coming from a sample. Remember, statistics come from samples. And so a sample mean is a statistic. And this is the actual formula that you'll see on the exam, that x bar is equal to the summation of x divided by n. And we literally will pronounce this guy right here as x bar. Okay, x bar. Please memorize that ASAP. Then we have a population mean. That's a parameter. And parameters, they usually get Greek letters, okay, to represent them in statistics. And so pretty much if you see a lowercase Greek letter in statistics, it's usually because it's a parameter. And so the Greek letter that we use to represent the population mean is this symbol right here. It looks like U, but notice here that you got this little extension of the one side, okay? And so we call this mu. And so it is vitally important that you memorize that mu is the population mean, and that's a parameter, and that x bar is the sample mean, and that's a statistic. So remember, with inferential statistics, what's going to happen? We want to know about this, but we're not going to measure it directly. Okay, that's too hard because we're not going to take a census too often. So what are we going to do? We're going to take a random sample, and so what are we going to actually calculate is x bar, and we're going to use the value of x bar to understand mu. That's ultimately what we're going to try to do. But unfortunately, that's not going to happen until about chapter 8 and a little bit, and again in chapter 9. Okay. So we got x bar, we got mu. Please memorize them. How about the median? The median is the midpoint of the observations when they are ranked or ordered from the smallest to the largest. And so this is a different way of measuring the center of the data. So this is all about the number of observations. And so it's the midpoint of the observations, okay, once you put them in order. So how are we going to determine the median? How are we going to calculate it? Okay, so what we're going to do is you got to take your data and you got to manipulate it a little bit. Because what are you going to have to do? You're going to have to put the observations in order of their size. You're going to have to rank them. You're going to have to order them from smallest to largest. And then, if the number of observations, n, that's called the sample size, is odd, all right, if it's odd, then the median is the middle observations. That's an easy one. So if n is odd, we're just going to go look for the middle observation, and that middle observation, there it is, that's the median. You even get a sound effect today. And then if the number of observations n is even, then the median is the average of the two middle observations. Okay, so what do I mean by, let's say that the two middle observations when we determine it are 4 and 6, and so to average them you would just add them together and divide by 2, and you would get 5, right? And so that's what I'm talking about when we're talking about averaging the two middle observations. Now I'll show you how to do all this stuff here in an example. So let's say that we took a look at 9 nations and the CO2 levels, pollution levels for those 9 nations in metric tons. Okay, so here are those countries, and unfortunately the U.S. is way above everybody else at 18.9. The closest one is Russia at 10.8 now. These numbers were taken, I think, about 8 years ago. So they may have changed significantly, but this is data from about 8 years ago or so. All right, so we have our 9 nations, okay? Problem is, if we're going to calculate the median, we can't use the data the way it stands right now. Why? Because we did not rank them. We didn't order them. We didn't put them from smallest to largest, okay? So when we calculate the median, when we go find it, we got to remember to order the data set. So here's our data again, and so what we're going to have to do is we're going to have to order them, and that's what I've done over here. So notice 0.2 is the smallest, all right, and then 0.3, and then 0.9, 1.4, and so on and so forth. So you'll just have to do it, okay, all the way up to 18.9 in the United States. So notice our data now is ranked, all right, and now we can go find the median, all right. Oh, I already gave you the answer. I didn't mean to do that. So let me show you how to do this. Now, there are formulas to tell you where the middle observation is, but if I don't have to give you a formula, I'm not going to, okay? And so once you order the data, in order to figure out the middle, basically we're going to start crossing out. So I'm going to cross out 0.2, the smallest with the largest, and then I'm just going to keep on crossing out, all right? And eventually I get to that guy right there that sits by itself, all right? And so what is that telling us? That the median, the median is equal to 1.8 metric tons per person. That's the median here, okay? So n here, remember n is odd, okay? And since n is odd, the middle observation should be your median, okay? Now notice what it did. It did its job. Here's 4 observations before it. Here's 4 observations after it, okay? And that's what the median does. Remember, it's based upon the number of observations, okay? And it's separating the data set into 2 equal parts, okay? Number of observations before the median, number of observations after the median should be equal, okay? And in both situations, we have 4 here, 4 observations here, 4 observations here, and so that guy right there would be the median. Let's say that I, instead of having 9, let's say I made the data set only have 8. Okay, I took a look at the top 8. And so I threw out the bottom one. I think it was Argentina or something. And so now, notice n is even. I'm going to have to do something different. What are we going to have to do? We're going to have to average the 2 middle observations here. Okay, so here's our data set again. It's just that I threw out the 0.2, okay, because we're only looking at 8 nations now. So we got 1, 2, 3, 4, 5, 6, 7, 8, okay? And so we're going to have to find the median. So we're going to do exactly the same thing. We're going to cross out the smallest with the largest, okay, instead of using a formula. And what are we left with? We're left with these 2 middle observations, and so we're going to have to average those 2. And so, there's our data set again. And so we're going to have to average 1.8 and 1.9. So you could do that in your head, put it in your calculator. I don't care. So you got 1.8 plus 1.9. Now, when you put that into your calculator, you're going to have to remember that you can't just put in 1.8 plus 1.9 and then hit your division side and divide by 2. Calculator is going to follow the order of operations, and so what you got to think of is that there's actually parentheses up here, okay? There's parentheses. I'm going to talk about more about that when we talk about standard deviation in the next section with regards to formulas. But for right now, note, when you put this in your calculator, you're going to have to put parentheses around here. So you're going to have to put parentheses 1.8 plus 1.9 divided by 2, and I think you're going to get 1.85 metric tons per person. And that's the median. Okay? Now, what I've done here is I made the United States ridiculously large. I made it really, really obvious that now it was probably an outlier before, but it's definitely an outlier now. Okay, if I artificially changed it to 1,800.9 instead of 18.9, it's a ridiculously high outlier. Okay, what would happen to the median in this situation? Can you think it through? What would happen to the median? What'd you say? What'd you say in your head at least? Did you say it's not going to change? Okay, and that's absolutely true. The median would not change in this situation because we would cross this with that, we'd cross out this with this, cross out that with that, and we would still get 1.85 metric tons per person. Okay, so the median was not affected by an outlier. And they're generally not. Okay? They're not going to be affected by outliers. Right? So what we say is that the median is resistant to outliers. Okay? So resistant in statistics means that it has these outliers have no effect on that particular statistic. So the median is resistant to outliers. When the outlier is present, it didn't change its value. It acted just like any other observation would. Okay. However, what would happen to the mean? I have here, but the mean isn't resistant to outliers. What would happen to the mean? In this situation, the mean would be a lot higher. Okay, it wouldn't be anywhere near 1.85. It would be extremely affected by this value right here and make it a lot larger. Okay, so the median is resistant to outliers, but the mean isn't. Okay, so I have a bit of a rule of thumb here. It says here, use the median for a measure of center if the data contains extreme outliers. Okay, so if your data contains extreme outliers, all right, we'll make it obvious when it's really extreme. But we're going to use the median for a measure of center if the data contains extreme outliers, like in here, all right? But for all other situations, use the mean for a measure of center, okay? So most of the time we are going to use the mean, okay? 90-95% of the time, we're going to use the mean, okay? But in those cases when we do have extreme outliers in our data, might want to consider using the median because it's going to be unaffected by that outlier or outliers, all right? So I would memorize that one, okay? Well, hopefully it just makes sense to you. You don't even have to do a whole lot of memorizing, okay? By the way, the median doesn't have a standardized symbol to it. Different textbooks will use different symbols to represent the median. So if it's not a standardized thing across all of statistics, I'm not going to give it to you. Okay, I'm not going to give you a symbol to memorize. Okay, X bar and mu, those are very standardized symbols that we use throughout statistics. But we can't seem to come up with a standardized symbol for the median, so I'm not going to give you one here. Okay, so no symbol for the median that you have to memorize, at least not for this class. Okay, so the shape of the distribution influences whether the mean is larger or smaller than the median, believe it or not. So what am I so remember the different shapes we have. We have bell shape that's symmetrical, we have skewed right, and we have skewed left. Those are your basic shapes that we talk about in statistics. All right. So if you have a perfectly symmetrical data set, what that's going to tell us that the mean equals the median exactly. Okay, if it's perfectly symmetrical. But what did I tell you about real data? Real data is not going to be perfectly symmetrical. However, is the mean and the median going to be far off even in that situation? So, okay, it's not perfectly symmetrical, all right? It's approximately bell-shaped, it's approximately symmetrical. That means, in that case, the mean will be close. It'll be pretty close to the median, okay? So the mean will be approximately equal to the median in that situation. Okay? How about if the data is skewed right? So if the data happens to be skewed to the right, so what kind of situation do we have here? Skewed right. Remember that's the way the tail is pointing. Okay? So we don't have many observations down here, but these would be the outliers. Okay? So the mean is going to be larger than the median. Now let's think about this. Here's the outliers. Okay? So here's outliers. And what did I tell you that the outliers do to the mean? Generally speaking, the outliers pulls on the mean, right? And so that means the mean is going to be, we would expect the mean to be located somewhere in here. Remember the down here is the values of the observations. So we would expect the mean to be somewhere around in here. Why? Because that's where most of our data is located. So we would expect the mean to be located right around here. But what did the outliers do? It pulls on the mean. And so it's going to make the mean move a little bit that way, further away from the typical data. So the mean might be located right here. I'm just going to generically put a point. Okay, so maybe the mean is going to be generically located here, all right? And the median, the way you got to think of it is that there's going to be a point on this axis where we can draw a straight line straight up, okay? And we have 50% of the data here, all right? And we have 50% of the data over here. And so if that's the case, that's basically a definition of the median. So the median would be maybe located right there. And so notice that the mean is larger than the median in our data set, okay, for skewed right. What about skewed left? What we find out is that the mean is smaller than the median. Okay, so let me get my pen back out. Looks like I gotta do a little bit of erasing here. And it shouldn't take me too long. So now I have to draw a distribution of data that isn't skewed right, it's skewed left. So hopefully you remember what that's going to look like. Alright, let me get the pen back out. This is going to be a little harder to draw, because we don't generally draw right to left. Well, that wasn't too bad, especially with my keypad here. So here's skewed left, okay? And so what's happening here? What's going to be out here? Here's going to be the outliers. What do the outliers do to the mean? It pulls on the mean, okay? So these outliers are small in value versus the rest of the data, because remember, this is a number line down here. Maybe we'll say this is 0 to 1,000, okay? And so these values down here are really, really small versus these values over here. And what do those outliers do? It pulls on the mean. And so it's going to make, so we would think that, well, mean should be located around here if it wasn't for those outliers. But because of the outliers, it's going to make the mean travel that way down the number line. So maybe the mean is going to be located right there. I don't know, I'm just generically putting a spot there, just far enough away from where I'm going to place the median, so it's obvious what I'm talking about. So then there's going to be a point here, maybe right here, where the median is going to be located, and we would draw a line, okay? That means we have 50% of the data here, and we got 50% of the data over here, all right? And so what's going on there is that the mean is now smaller than the median when you have skewed left data. Okay, so you can visualize how all that's working. Okay, and this is an illustration out of the book about exactly what I just talked about. Okay, so it says here in a skewed distribution, the mean is farther out in the long tail than the median. Okay, so here, here's the so there's no tail here with bell-shaped. Okay, that's symmetrical. All right. And here's the tail. That's where the mean's going to be pulled over by, into a little bit towards that tail. And here's the tail for skewed left is down here. Mean's getting pulled over that way, okay, versus the median. Okay, so either you got to memorize that that relationship, or you can just simply draw your you can draw these skewed distributions and just sort of think it through based upon graphically what's going on. It's up to you. Okay? So that's the end of our discussion for this section. Thank you.